Hi guys, I am Doc. Welcome to my video series 5 Minutes to Geek. Today we would be discussing about feature transformation and kernels. Okay, let's get started. So what was the problem? So actually we know that in the SVM, we know that in SVM we have a linear model, right? So SVM is a linear model, and there is so everything which is input to a system in the SVM, this input should be linear, because SVM is a linear model. You can process the linear data only. So whatever is the input to the system should be linear only. It's like saying something that, for example, I have a car, and I know that this car will run on the gasoline. So this car requires a gas as an input, and it will run on this gas. It doesn't matter to me how this gas is being extracted. For example, if I am said that I have a petroleum available and I want the petroleum to be put into the car, and I want the car to find itself a way to extract or transform the petroleum into the gasoline, then it won't be able to. So what happens is that uh, what happened is that the same way in the SVM itself, if I would say that I am giving a non-linear input, and I am saying that as I am asking SVM to work on it, SVM would say no, oh man, I won't be able to work on that. So actually, it's not a SVM's problem to convert non-linear data into a linear data or the data transformation. So actually SVM says that give me the input that should be linear. I will give you the output that I think will classify the two classes. Okay. So the problem was that being SVM a linear model, it is not be able to not able to perform classification on non-linear data. So here's the kernel comes in. Okay, so actually this is a non-linear data which I've been given. So there are two basically features, x1 and x2, and as you can see, these two features are non-linearly related. How can I say it? They are non-linearly related because they are not in a straight line. As simple as that. So as you can see, this is a non-linear data, and if I would try to give it to the SVM, and I would say that if I would try to give it to the SVM, and I would say that is it is an input to the SVM, then SVM would try to create a classifier on this data, and it won't be able to create a good classifier. It will create a classifier like this, or it will create a classifier like this, but in either how, these classifiers are not able to group group two different points, or it is unable to divide the 2 points into different classes. The actual classifier which exists is somewhat like the radial classifier which should exist here, and SVM is not able to process the radial classifier unless radial classifier, as SVM is a linear model. So this brings us to the need of transforming this nonlinear data into the linear data. So now what happens that I want to transform this data something into a linear type. For as you can see, there is a linear boundary which helps us separating these two data. So I can say that these two data are linearly related. Okay, so I am transforming this data, and transforming is data such that these two axes would become x1 prime and x2 prime. Actually, you can see the third axis there. We will come to it later, but let's say that we have x1 and x2 are the two features which were non-linear related, and we transformed it somewhat in x1 prime and x2 prime so that they are now linear related. For a rough guess, what could be the transformation be? This transformation could be, let's say, x1 square, and let's say this 2 is x2 square. So actually x1 prime is equal to x1 square, and x2 prime is equal to x2 square. So it's a so basically it's a typical equation of circle, and we say that typical equation of circle is x1 square by a plus x2 square by b equal to c. I can say this is a typical equation of circle, or I can say typical equation of ellipse. In the case of circle, a and b would be same. In case of ellipse, the a and b would be different. So actually we are moving, as we see that the data is non-linearly related and it's typically seems to be a circle, so we transform it into, so we actually moved into the non-linear plane. As you can see, there is a linear plane, x1 and x2 was a linear plane. Now we moved into the non-linear plane where x1 prime is actually x1 square and x2 prime is x2 square. We moved into a non-linear space, and then we saw that, oh, it's actually a linear. When we moved to the non-linear space, we actually saw it's linear. So this is a transformation which we are seeking. Okay, moving from linear to non-linear space, is it a free pass? Obviously no. There are some consequences from moving from linear to non-linear space. Let's say it. Okay, so actually I have two features, and I have a transformation degree 2, as I have seen here. I have actually two features, and I am actually transforming the space from linear to the quadratic space, right? So what happens is that we introduce more features. For example, I have only two features, x and y. When I move to a quadratic space, and the quadratic space equation is defined as ax square plus by square plus cxy plus dx plus ey plus f equal to 0. Actually, two features are now converted into the six features. This is a complete equation of the quadratic space. Any of the coefficient can be 0, it doesn't matter. If but it can be 0, or it may be 0, or it may not be 0. So we are taking a complete quadratic space, and we are saying that two features have been transformed to the six features. So actually there is a feature explosion when we move from a linear space to the I would say a non-linear space. So if I will move from non linear space to a non-linear space, and we are moving with the two features to a basically we are moving from linear space to a quadratic space, that is a transformation degree of 2. If I would say I have actually four features, then four features would convert into 15 features in the quadratic space. If I would say that I have a degree of 3, then actually these two features would be ax cube plus by cube plus cz cube plus axyz plus plus bxy plus xz plus czy. So there we would be introducing much more features in the transformation degree of cube. So when we move from linear space to non-linear space, there is actually feature explosion which occurs. Okay, the same is which we see here. So actually we have two features available. When we move to the linear space, when we move to the quadratic space, where we say the x1 prime and x2 prime are basically the quadratic values of x1 and x2 quadratic power, then we introduced a new feature space here. Okay, so how to do it in Python? So basically we know that the kernel is responsible for the transformation of this linear model of this anything non-linear data into something linear data, and this linear data is being fed into the SVM model. So the problem which was there is that we have been given something like quadratic data which is being given, and I said that I will put a kernel before SVM which will be responsible for conversion of this quadratic data into linear data, and it will convert this quadratic data into linear data by transformation of the features, and it will feed that data into the SVM, and SVM will further because SVM is getting input as a linear data, it don't have to worry upon what are the input feature and what are the other things and how the transformation was taken care by the kernel. It don't have to worry about anything, and it will simply give the classification. After getting the classification, after getting the class of a particular data, we can map it back to the non-linear data. For example, after the class is given c1 as an output, we can map this c1 back to for the this c1 class was given for the new feature space. This was actually the input data. We converted using the kernel into the feature space, which is actually much more than the input data, and we converted into the feature space, which was fed into the SVM, and SVM gave the output as a class C1, and this C1 was mapped back to the input data. So how the this is how the whole chain works. Okay. So the question comes how to do this in Python. So the basically when we initialize the SVC object in Python, we provide the kernel with this. We say if we say the kernel is linear, then we say that the actually don't do anything on the data, and data is my data will become my feature space itself. So there is no transformation needed on the data itself. So actually I am saying the data is linearly separable. So if I draw a straight line, I would be able to separate the two classes which is available in the data. Okay, so now if I say that my kernel is actually polynomial, so and I can provide the degree. For example, if I'm giving the degree 3, I can say that the my work I want to transform the data into the cubic degree, like we saw earlier. How it will find out all the coefficients for transformation, that's out of scope, and we have to dig into the maths for that. So it's basically taking the kernel as polynomial, we define it, and so if there is some non-linearity in the data, we can define the polynomial polykernel for the SVC with its the degree. If we say there is something circular or something radial present in the data, then we can provide RBF as a kernel type, and it will take care of the circles or ellipse which are available in the data, or some radialness which is available in the data, like this curves and other things it can take care. So for the nonlinear transformation, these both kernels are being used, and by providing the different value of kernels, we can achieve this in Python. And by saying Python, I am referring to the sklearn library. Okay, so let's see RBF in some more detail. For example, there are few other parameters which are taken input in RBF. Apart from the kernel, in all the SVC, we can provide the value of C. The value of C which we discussed earlier, the higher the value of C, we are saying that actually we need the higher the value of C, we need less misclassification, and we need stricter boundaries between the two classes. So higher the value of C, we ask for the less misclassification, move to the more overfitting model, and in the lower the value of C, we are moving toward the more generalizable model. Okay, so here we can see if we keep the C same for three of them, there is one more input parameter which is being taken. The other input parameter is gamma for the RBF. The gamma basically tells what is the influence of a particular point to its surrounding. So how far is it, the lower the value of gamma, the farther is the influence of a point to its surrounding. So if I keep on increasing the gamma, the influence of the points reduces, and actually it reduces much enough to only its local neighbors. So this seems to be a perfect good this seems to be a good, I would say, group or cluster which has been formed here. Okay, so similarly when we change here, we are increasing the C. This image has been taken from the sklearn official page, and similarly here we are increasing the gamma factor. So as we can see, as we increase the gamma, the influence of the point decreases. As we increase the C, there is a lesser and lesser misclassification, and stricter boundary of the classifier which is created is much more stricter between the two classes. This seems to be the perfect for the value of C and G. This classification seems to be the perfect. Okay, if you have any question, put it in the comment section. I will try to reach as soon as possible. If you like the video, please hit the like button, and for more such videos, subscribe and hit the notification bell icon. Thank you.